With this experiment that we did in earlier section about the Galileo's thermometer, we understood that we have droplet of the gas which is supported by droplet of a particular fluid which is supported by the gas in a column of small pipe of some kind, and it's a transparent, so you can see the motion of the droplet which is supported by the pressure and volume with the temperature being varying with the time. So, and as you know, as it becomes to a particular equilibrium, then you can calibrate the thermometer. But earlier we also looked at some of these processes which are connected with the ideal gas processes. So, very quickly let us review using the first law of thermodynamics, what are those 4 processes, and now we are going to embark into the thermodynamic potentials. So, if you look at on your slide, I have created a comparison chart where you have isothermal process, which is T is constant, and because in the isothermal temperature has to be constant, and that is where if you look at our equation which is says Q plus W is equal to delta H. That was the general statement of first law of thermodynamics, Q being heat, W being work. So, in this case, because the temperature is constant, Q becomes equal to the work, and that is where you can define the work term in terms of the ideal gas law. PV is equal to mRT, and because we know the temperature, we can work it out based on the volume changes as we are keeping the temperature constant. And so, if there is a isotherm and you are going from volume V1 to V2, you are essentially expanding this particular gas, and the area below that curve is the work done. Now, if you look at the constant volume, what happens then? There is no change in the volume, there is no work done. So, it is a straight line in the PV curve. We are always looking at the P versus volume curve, and as you know, the states of the thermodynamic variables can be defined by 2 variables, and normally they are multiplication of intensive and the extensive variable. So, intensive variable here is pressure, extensive variable is volume. So, if you look at isochoric model, then volume is constant, Q then becomes equal to delta U, that means heat supplied is equal to the change in internal energy, work is 0, and then Q we can now calculate in terms of the specific heat at constant volume, and that goes to N CV delta T. Now, if you go to isobaric system, then we said okay, we are going to go between 2 isotherm, and that means we are changing the temperature, however, we are keeping the pressure constant. As the gas goes from temperature 1 to temperature 2 in a quasi static equilibrium model, that is where we can look at the pressure being constant and then volume going from V1 to V2, and if it is the same process of expansion, the work done under that constant pressure, which could be a piston providing an equal amount of pressure as the volume of the gas changes, that in that case the delta U and Q and W are related by Q is equal to delta U minus W, and W we know from earlier experiments is equal to pressure multiplied by change in volume V2 minus V1, and Q is given by NCP in this case delta T, because Cp is the constant pressure specific heat. As we know, specific heat is different for constant volume Cv and constant pressure Cp. So, in this case, now with this isobaric process you can relate between Cp and Cv, which is Cp, which is the specific heat at constant pressure, is equal to Cv plus R. Now, with that understanding, now we go to adiabatic process, where essentially the system goes from temperature 1 to 2 in rather succession without any loss of energy, and in that case what we are looking at, Q is equal to 0, delta U internal energy equal to work, but in this case it is not connected with the linear relationship pressure multiplied by P2 V2 minus V1, because pressure is also changing as the volume is changing. In isobaric method you saw that pressure was constant, so the integration was rather simple and you could keep P outside and integrate over V2 minus V1, but in this case it is a complicated integration, and if you look at that, it also has an exponential component, and so it becomes a P V to the power gamma, which is ratio of Cp over Cw. So, with that understanding, now we are ready to launch into cyclic processes, and any cyclic process is looked into the graph between P and V, which are again between intensive variable P and extensive variable V. And if you look at that cyclic process, you go from point A to point B, and if you look at that, now we can calculate work done. So, there are two situations. When you go from A to B, the work done on the gas is the entire shaded area, because this is the entire work that you have done. If you go to another part, when you are starting from B and going to A, then the work done is again is below the area of the curve, which is B and A, which is the shaded area here. But if you look at the net work done from going from A to B and B to A, then the cyclic process as net work done is the area which is inside this particular cycle, and that is what we call W net. Once you have W net, then you have the concept of efficiency, where you now know is that how much total energy was given to go from A to B and B to C, and then if you divide that by W net, then you can calculate the efficiency of the system. So, this is how the efficiency of systems are calculated. But if you look at in the cyclic process, combine the basic process of other thermodynamic processes. Now, you look at it's like an engine. So, the reason we come up with cyclic process is we are looking at the situation of the engine, where there are various cycles. Compression, so you start with getting the gas into the cylinder block, and then you essentially look into immediately you have a spark plug. I am talking about the old engines, internal combustion engine. Those days they used to have spark plug. So, when you spark plug, then what will happen? There will be expansion of the gas. Once the gas expands, at that point, then it is ready to compress, because the crankshaft is going to work backwards. So, now we are looking at the constant temperature process, constant volume processes, and also in some cases constant pressure processes. So, combining all these things, we can design different kinds of what we call heat engines, and that is the idea of system which are cyclic processes. And if you look at natural system like sound waves, also happens, there is a compression and decompression cycle. The reason you can hear my voice to your ear right now, because the air between your system and your ear, where the audio is coming out, is becoming compressed and rarefied, and this is the process of compression and as well as expansion that is creating a standing wave, and that wave is getting to your ear, and it is also creating the same kind of engine within your ear, so that you can reproduce that sound in your brain. So, this whole process is very generic. So, you should not only think about thermodynamic heat engines, but you can also look at all kinds of natural systems. They form the engine kind of or cyclic processes, and then work done is in the cyclic process is the area inside this cyclic process. Now, let me introduce a concept for the gas, which is a very, very important concept, which is called Boltzman, Maxwell-Boltzman distribution. So, we looked at the gas of different kind, and we put different kinds of temperatures on it. And what we found in that kind of situation, that if you change the temperature, and if you look at the distribution of different velocities of the particle, and that comes out of the idea about the kinetic theory of the gases, that there is a distribution of velocities on each particle. And as you go to higher temperature, the distribution becomes much wider and wider. So, now we are in the cyclic processes, because we are going to connect that with the molecular dynamics. We also want to understand how these gases which are being compressed and then expanded, and different processes are happening which are isothermal, isobaric, isochoric, and also what we call isentropic or rather adiabatic processes. So, for that you need to understand how the molecules and atoms are going to behave inside that gas chamber, which is going through a cyclic transition of thermodynamic kind, and that is where you need to understand that Maxwell-Boltzman distribution tells us, as you look at on your slide, that if you have a higher temperature, then you have a lot more distribution of velocities as compared to as I go to the lower temperature. So, this peak as you are seeing here is becoming sharper and sharper as I go towards lower temperature. But as I go to higher temperature, then the velocity distribution will be much more wider. And based on this, you come up with an exponential function which gives us good idea about, because it is an exponential curve here. With that exponential term we can calculate the temperature by equipartition theorem, which we had talked about. So, high temperature distribution is broader. So, average kinetic energy now you can calculate, which is half mv square from the Newton's laws of motion. But if you look at the distribution inside this exponential curve, which increases first and decreases later on at a central point of that temperature, that is when we look at 3/2 kT. And if you look at the velocity at particular temperature, the thermal velocity as we call, then it connects to the thermal speed, and that comes out to be 3 kT/m, where k is the Boltzmann constant. And I think that is where in the kinetic theory of gases, Maxwell-Boltzman came up with a distribution function, and that distribution function was then related with what we call Boltzmann constant, and that allows us to use now this whole idea in a cyclic process with the kinetic theory of gases, with the Maxwell and Boltzmann distribution of the velocities to calculate temperature, and that comes out with the velocity, what we call thermal speeds of the particles. So, let me stop here, and we are now going to consider other parameters in terms of thermal behavior of the systems. Thank you.